Hi and welcome to this Behind the Effects video, which covers some of the fundamentals of the physics-based combustion solver in Bifrost. More specifically, we'll be having a look at the math and some of the physics-based models behind the solver. And before you watch this video, I highly recommend you have a look at the video by Robert Britson, where he discusses some of the math behind the aero solver. So in his video, he introduces some concepts and terminology that we will also use here. So this video is not really about how to set up simulations in Bifrost. It's more about the technology behind the scenes. But hopefully it will give you some intuition about what goes on in the solver itself. And this may guide you as you start to run simulations on your own. So before I go into some of the more technical detail, I just want to touch briefly on the motivation and essentially the ultimate goal behind the Bifrost combustion solver. So what we're striving for is essentially to provide the user with physically plausible results by default. And what this means is, for example, that if you have some real-world footage that depicts some fire or combustion phenomena, and you happen to know the real-world conditions, to some extent at least, that resulted in these fluid or fire phenomena, then if you replicate those conditions in the Bifrost solver, then ideally the results should come qualitatively close to what you observed in the real world. And another important aspect of any physics-based solver is, of course, the high-level artistic control. We're still aiming for high-level artistic control being easy, but on the other hand, the user should not struggle with high-level artistic controls if what they're working towards is something that is physically plausible or correct. Only when it's required to work towards something that's non-physical should it be required to do all kinds of manual tweaks and controls. So we're not quite there yet, but this is the motivation and essentially the ultimate goal that we are working towards. So as I mentioned on the previous slide, we're striving for physical realism by default. And one of the steps towards this goal has been to include more physics-based models in our underlying solver. And this is also one of the things that sets the Bifrost combustion solver apart from other solvers in graphics that are out there. So I've listed some of the things that we've included in the solver on the left here. So at the top, I've listed the ability to use real-world fuels, and we also make use of their actual measurable physical properties in the underlying solver, which means that, for example, we can reproduce the adiabatic flame temperatures if we know the fuel, for example, and the ignition temperature. We've also looked into some of the models that were developed in the CFD communities, and we've adopted some of the models that were developed for soot formation and soot oxidation. And one of the really nice properties of these models is that they were validated against real-world results. We've also looked into expanding the range of radiative phenomena that we can take into account. So in graphics, it's typical to take radiative cooling into account, and this is what gives you the nice look of flames as they cool very rapidly. But radiative heating is, in the real world, also a very important thing to take into account if you want to achieve accuracy. And in some cases, for some types of simulations, the radiative heating contribution is similar in magnitude to the contribution in heat you get from the convection, which is also another important part. But for graphics, we've also found the radiative heating to give rise to some interesting visual phenomena, and I'll come back to that a bit later on. So we have also developed a condensation model, and what this allows us to do is, as the solver solves for the combustion of the real-world fuels and oxidizers, it will also track the amount of water vapor that was produced. And if we then couple that with the condensation model, we can model the vapor as it condenses and then render this out in a physics-based renderer. So one of our key focus points has also been that this is not a solver for CFD, this is a solver for graphics. And in graphics, it's really important that we have the ability to quickly evaluate results. So we must have the ability to take large time steps, even though in reality a lot of the physics is taking place on a very small time scale. But it has been a key focus of ours to develop solvers for the ordinary and partial differential equations that are involved that facilitate taking large time steps. So on the right here you see a simulation that was actually simulated in Bifrost, and which includes many of the components that I described just now. So we have physics-based soot formation, physics-based soot oxidation. You see that it's a non-smoking flame. Above the flames you see the water vapor condensing, and then we also have radiative heating and radiative cooling on. Okay, so let's now have a look at the dynamics behind the combustion solver. So essentially the combustion solver is just an extension to the aero solver, and Robert already covered the math behind the aero solver. So they're based on the same fundamental equations, the incompressible inviscid Euler equations. And there are two components to this. So there's conservation of momentum, which you can think of essentially just as Newton's second law, F equals ma. And then there's conservation of mass. Now, Robert already touched on the conservation of mass or conservation of volume, and you model it with the partial differential equation like this. The divergence of the velocity, which measures volume change, is equal to, in our case, something on the right hand side called phi. Now in the case of a smoke solve, phi would be 0. There would be no volume expansion over time. But in the case of combustion, we'd like to model things like explosions. We'd like to model air expanding as it heats up and contracting as it cools down. On the other hand, we don't want to enter the fully compressible regime, where we need to solve the compressible inviscid Euler equations, because those are much more complicated to solve and time consuming to solve. Now, fire and combustion is really a complex interplay between thermodynamics on the one hand and then fluid dynamics on the other hand. So the fluid dynamics is represented by the inviscid Euler equations, and to couple the thermodynamics and the fluid dynamics we use an equation of state, in our case the ideal gas law. Basically it computes the fluid mass density, rho here, as a function of the pressure divided by the specific gas constant times the temperature. Now here it's important that we decouple the density and the pressure. That's to avoid introducing a speed of sound, which would incur lower time steps and thereby a slower solve, which essentially we'd like to avoid for computer graphics. So we decouple the density and the pressure here, and in our case we use a constant pressure when we evaluate the mass density, and we just use the pressure of 1 atmosphere. And that is justified if you have simulations that are not contained but can freely expand. And you could also imagine using other types of decoupled pressures where they depend on the height into the atmosphere, for example, which would mean that you could use it to model things like clouds or nuclear explosions. Now, the thermodynamic part is represented by the thermal energy equation in our case. And essentially this models conservation of energy. But again, to avoid entering the fully compressible regime, we simplify it a bit. And in particular, we're not going to model things like compressing a fluid will heat it up. And that's again to avoid entering the fully compressible regime, as I said. So we've thrown away some contributions, which means that we do violate the first law of thermodynamics, but for graphics, we assume that this is okay. We're not really interested in graphics in the energy itself, but rather we're interested in the temperature, because we can use the temperature to render things with a blackbody radiation model, and we can feed it into our buoyancy models and so on. So energy and temperature are coupled by the specific heat, Cp here. And on the left-hand side, we have the material derivative of the temperature, which includes both the local change in time of the temperature and the convective effects. So convection is one of the fundamentals of thermodynamics, and it's included, as I said, in this part. So Robert went into some detail with the material derivative, and I'll refer to his talk for more details about exactly what it looks like. On the right-hand side here, we have some of the contributions that we are modeling that contribute to the change in temperature. And the first contribution here is conduction. So basically, when two objects of different temperature come into contact, now the contact part is important, then you'll have a heat flow between the two. And heat flow is specified usually with a flux, and then we apply the divergence operator to it here to compute the total outflow of heat due to conduction. And then the second term is a source or sink term. Well, in the case of combustion, actually a source term, because combustion is an exothermic process which generates heat. And then on the final term here on the right, we have the radiation, which can either be a source or a sink, because we have both radiative cooling and we have radiative heating. Now, in addition to all this, we also model diffusion of species, like oxygen or fuel. And in particular, diffusion of oxygen is important because that allows us to model diffusion flames and soot oxidation. So let's now have a look at some of the volume expansion and compression effects that we can model with the simplifications that we've made. And as I mentioned on the previous slide, we'd like to model volume expansion due to explosions, and we'd like to model volume expansion as the air heats up and volume compression as the air cools down. And this is captured by this equation here, which was proposed in this 2003 paper. It was the divergence of the velocity equals some phi. As I also said on the previous slide, phi equals 0 means that there's no volume expansion. But if phi is less than 0, we'll have volume compression, and if phi is larger than 0, then we'll have volume expansion. Or what should we set phi equal to exactly to model this? Can we say something more principled about what it should be? So we went back and had a look at the fundamental equation for conservation of mass, which looks like this. And this equation is derived from the global conservation property of mass, which states that mass cannot be created out of nothing and it cannot just disappear. So it must be globally conserved. And if we look at a single point in space, or in our case, for our solver, let's say we're looking at a voxel, then this equation for conservation of mass holds. Basically, it says that the local change in mass, in this case mass density, but imagine that we integrated this over the entire volume of the voxel. So the change in mass density must be balanced by some flow of mass across the faces of the voxels. So if the mass inside the voxel is decreasing, this term must be positive. We must have some flow of mass out of the voxel. And this is captured by this equation. So now, if we actually expand this term and we fold some of the resulting terms into the material derivative of the mass density, move things around a bit, we arrive at this equation, which states that the divergence of the velocity field, which we want to set equal to some phi, is actually equal to this expression here. And this expression is just 1 over the mass density, minus in front, times the material derivative of the mass density. And this is what we actually compute in the Bifrost solver to capture the volume expansion and compression effects. But we of course also expose controls to scale this for artistic purposes. Here's a simple example of volume expansion in action, where an explosion is triggered as missile hits the ground. And one other thing I'd like to point out in this particular video is that Robert talked about the tile tree and how we had the ability to do adaptive and sparse simulations, and this particular video illustrates that. So the missile trail and the explosion were all the same simulation, and that was facilitated by the ability of the Bifrost combustion solver to actually run on adaptive and sparse regions of space. Okay, so we've now discussed some of the dynamics behind the combustion solver, and I'll now discuss some of the components that contribute to the change in temperature via the thermal energy equation. So first I'll discuss the combustion reaction itself. So as you can see here, I've written the combustion reaction as a single stage reaction, which takes some amount of fuel, which can be, in the case of the Bifrost solver, currently some gaseous hydrocarbon fuel like propane. This fuel then reacts with oxidizer, which might be some arbitrary mixture of oxygen and nitrogen. Other gases can be involved too, but it's really the oxygen that reacts with the fuel. Then these two constituents react and produce water vapor, carbon dioxide, soot, and heat. And the heat then feeds back into the fluid dynamics. As this reaction goes on, we use the real-world measurable properties for a lot of the processes that go on, and I've listed some of them here. One thing to note is that in the real world, the reaction process is a really complicated entity, and there are many intermediate species and reactions going on, and all these take place at a very small time scale. But we're not really interested from a graphics point of view in modeling all of these. We are more interested in the final product. So once the combustion reaction starts, the flame will start to propagate throughout the fuel, and a model that's typically used for volumetric combustion in graphics is just to use a reaction rate model where you transform the fuel into products based on some either linear expression or an Arrhenius expression. But what we found, and what is consistent with the approaches taken in CFD, is that if you really want to model this accurately and get the correct flame propagation speeds throughout your fuel, you need to take very small time steps, and you need to also model all these intermediate reactions that we're not really interested in if we can get away with it. So instead, we've adopted the thin flame model, which was also introduced to graphics in 2003. Now I've written the equation for the flame propagation speed here, and it's just a level set equation. So if you look at phi here, imagine that this is a signed distance function. It changes over time, and it propagates with some speed, which is this Vn here. And Vn is the flame propagation speed. Now, in the 2003 paper, they used constant flame propagation speed. They evolved the equation over time with a method that had a strict CFL condition. Now, this is a very accurate approach, but it has also the limitation of the constant flame speed. So in our approach, we took outset in some experimental data back from the 50s and 60s. So back then, a lot of measurements were made of the flame speeds of various fuels combined and pre-mixed with oxidizers. And we interpolate and extrapolate this data based on the local concentration of species, such that we get, when we interpolate the data, we get data that's experimentally valid. When we extrapolate, of course, we move beyond what is documented in the literature, but it stays within what is physically acceptable or plausible for graphics, though it may not be fully accurate. So we allow, in other words, this Vn to vary in time and space. Furthermore, we assume that the norm of the gradient of phi here is 1, which it is up to some truncation error for distance field that we've computed numerically. And then we move this term to the right hand side and we arrive at this equation, which is a lot simpler, and it's just a dilation essentially. So the thin flame is propagating by means of a dilation. Of course, it's not as accurate and it may not give fully correct results if you have high spatial variation in the flame propagation speeds. We do also support the more complicated level set advection scheme or propagation scheme, but by default we use this approach, which is not restricted by the CFL condition, such that you can take arbitrarily large time steps. And these flames can propagate at a very high speed, so if we really need to take the CFL into account for these flames propagating, it will seriously hurt performance of the solver. So I want to show that this thin flame setup, though in CFD it's mainly used for pre-mixed fuel and oxidizers, it can also be used to track a propagating diffusion flame if we combine the thin flame model with explicit diffusion of oxygen. So here's the experimental or the setup in Maya. We have a fuel source specified as a cylinder here at the bottom. We'll have a fuel plume rising. It's not pre-mixed with oxygen, but we have oxygen outside here in the surrounding air. And as the fuel plume comes in contact with the spark here, it ignites, and you'll see the flame propagating along the circumference of the fuel plume, and then it will continue burning as it rises. So here's the simulation seen from two slightly different viewpoints. I hope you could see that as the fuel plume ignited, the flame propagated along the circumference. It will then burn in these thin sheets, or generate these thin sheets of soot that are characteristic of diffusion flames, and this burning will continue as the fuel plume rises. So to validate the laminar flame speeds, we've also recreated an experiment digitally that was performed by the US Bureau of Mines in the 50s, and I briefly mentioned this earlier, that they performed these experiments of pre-mixed fuel and oxidizer to determine the laminar flame speeds of various mixtures. So we've, as I said, recreated this apparatus in Maya. Basically, we've simplified it a lot, I must say, because we are not limited by all the physical restrictions that they were when performing the real experiments. But basically, it's a cylinder that's filled with some mixture of fuel and oxidizer. It's then ignited at the bottom, and then the blue flame cap will travel up the tube, and that's what you'll see here in the video. And of course, this flame speed depends on the mixture, and we just compute the laminar flame speeds based on the concentration of the various species, so that the user is not required to explicitly specify these flame speeds. But then, of course, the user can override the flame speeds for artistic control. I'll just show the video that shows the propagating flames one more time. Here it is. As you can see, there's a wide variation in the flame speeds. Of course, in practice, the flame speeds can vary spatially and temporally. So here, what you see in white is fuel that's being mixed by turbulence and oxygen diffusion. We then place the camera inside this fuel plume and ignite, and this is what you see here. And now in slow motion, and I'll just loop the slow motion animation a couple of times, just so you can have a look at how the flames propagate throughout the mixture of fuel and oxidizer that was governed by diffusion and turbulent mixing. So beyond the actual combustion process itself and the thin flame model, we've also combined with radiative cooling and heating. And if we return to the thermal energy equation again, this time looking at it with only the contributions from radiation, then the left-hand side looks like this. We have the derivative of temperature with respect to time. This converts to conservation of energy. And then on the right-hand side, we have two terms. This term here models the radiative cooling. And this is what you typically take into account in graphics. You need to solve an ordinary differential equation, which you can do analytically. Basically, here, A here is the absorption coefficient, sigma is the Stefan-Boltzmann constant, and then we have T to the power of 4, and because T is over here as well, it's an ordinary differential equation. Now, if we want to take into account radiative heating as well, this second term is required, which is the absorption coefficient times G, where G is the incident radiation. And radiation is different from other types of heat transfer, like conduction, for example. If you have conduction, two things that are in contact you will have conduction or heat transfer between these. But radiation spreads throughout space and may heat up things at a distance, for example, causing fuel to ignite without heating up the air in between the heat source and the fuel source. And I'll show an example of that in a moment. Now, of course, we have AG here. Once we have established what G is, we can just solve this ordinary differential equation, quite similar to how we would solve it for just the radiative cooling contribution. But we need to solve for G. And to solve for G, we ideally have to solve the radiative transfer equation. And this is very similar to the rendering equation in graphics, which is very complex and difficult to solve. But luckily there are diffusion approximations to this that we can take advantage of. And we use a diffusion approximation called P1. There's a whole theory behind these Pn diffusion approximations that I won't cover here, but you can look into some of the literature behind radiative heat transfer to find out more about this. And the diffusion approximation looks like this. It's essentially just a partial differential equation for G. What complicates this is that this gamma here can become very large. The problem is that it's inversely proportional to the absorption coefficient. So in areas where A is very small, that is, in areas that are almost transparent, lambda becomes very big. So there was a paper published in Graphics in 2013. Actually, this is a rendering paper, but we can take advantage of it for simulation as well. It uses something called flux-limited diffusion, where you modify this gamma here based on A, such that this equation becomes numerically well behaved. The problem, though, is that gamma is nonlinear, depends nonlinearly on G, so this becomes a nonlinear partial differential equation. And to solve that, we use a nonlinear multigrid approach. So here's an example of what radiative heating can bring to graphics: ignition at a distance. So here we ignite a fuel source, which is close to but not in direct contact with another fuel source. It then, due to radiative heating, ignites the second fuel source, which then in this case travels along a torus where fuel was emitted and burns along that. So this is a combination of, again, many of the techniques I've covered in some of the past slides. We have the thin flame propagation, we have the radiative heating, soot formation, etc. So one thing I just want to briefly cover here is the blue flame you can see. So the blue flame, we model that with the reaction rate. This is where the reaction is actually taking place, and this is where you get this spectral line emission from the fuel as it's broken up into radicals. So another important part of the look of fire and combustion phenomena in general is of course soot. In graphics, it's typically done by forming soot proportional to the reaction rate. So the more reaction you have, the more soot you'll generate. And this approach was, for example, proposed in this 2003 paper. But there's actually a very simple scenario where this fails to model what happens in the real world. So if you look at the illustration on the right here, essentially this is a diffusion flame. I'll come back to what these individual bands mean later on, or in a bit, but this is the visual height of the flame, and it's yellow to red due to the glowing soot. And in the middle here we have the region where the reaction takes place, where we only have the blue flame but no soot. So the stoichiometric contour here, outlined with a wider line, is where oxygen and fuel react, and all oxygen and fuel react to form just products. So this means that in the region out here we have an excess of oxygen, and in the region in here we have an excess of fuel. We still have reaction going on in here as well, but there will be some excess fuel. So soot formation with the model from 2003 would actually generate soot out here near this thick line, but in reality soot formation takes place on the fuel rich side, not exactly at the stoichiometric contour but slightly inside it, and it's determined by these two upper and lower limits, where the limits refer to the mass fraction of fuel, and the mass fraction of fuel is higher in here than it is out here. So we actually expose these upper and lower limits in the Bifrost combustion solver, but allow the user to tweak them to determine, to either thicken or thin the band within which soot is generated. But in reality, soot is only generated in here and will then, of course, due to convection and other effects, buoyant effects, travel upwards and give rise to the sort of the glowing flame. So our model is based on a paper from 2011, which was validated for two types of real-world fuel, but it was then generalized to any type of fuel by means of this laminar smoke point height parameter, which you can look up for arbitrary fuels. And that's what we do in the Bifrost solver. We've looked up these tabular values and then used them to determine how sooty a particular type of fuel is. So the model you actually have to solve, or the equation you have to solve, is just a linear ordinary differential equation in this case, so it's quite similar and quite simple, and it depends on temperature and the mass fraction of fuel, Y fuel, and the laminar smoke point height of the fuel, and that gives you the change over time in the soot mass fraction. So here's an example of soot formation in action. No oxidation is going on here, so we have a smoking flame. Now, soot oxidation is the process where clusters of soot are attacked by oxygen, which in turn reduces the smoke and can give you something like a non-smoking flame, for example, a candle flame. And again, the soot oxidation takes place in a band which starts roughly at the stoichiometric contour and then ends either at the visible flame, where all soot will be oxidized, or the soot oxidation process stops due to the temperature becoming too low. So in graphics, the models used are mostly heuristic and not very well documented actually. There are no papers we could find, at least in graphics, that describe this. And our model is based on a combination of two models from CFD, one from 1977 and one from 2011, which were validated for these real-world fuels. Now, in this case, the ordinary differential equation is slightly more complicated than in the soot formation case. It's non-linear, but we can construct a semi-implicit solution using a separation of variables approach that allows us to take large time steps, which is important for graphics. And here's a simulation with soot oxidation in play, and as you can see, the soot oxidation gives rise to a non-smoking flame and really gives you all these interesting and complicated flame structures. Here's another example where a user has been playing with the amount of soot oxidation for artistic effects to create an interpolation between a smoking and a non-smoking flame. So we've also developed a simple condensation model. Of course, the goal here is really for graphics to just qualitatively capturing the effect of water vapor condensation, not necessarily to give you something accurate, but to give you something that mimics the visual effect and allows for high-level control. And we've based the model on the relative humidity. So basically, when the relative humidity is above 1, the water vapor will start to condense. And the equation for the relative humidity, I've listed it here. It's just the fraction of the partial pressure of the water vapor to the partial pressure of the saturated water vapor, which depends on temperature. And you can see the non-smoking flame here, but then the water vapor will start to condense as the smoke or as the air cools down. And that was it, basically what we choose to cover in this fundamentals of combustion in Bifrost. Thanks for listening.